Welcome, everyone. Today, we are diving into the fascinating world of Aves, commonly known as birds. Imagine being tasked with building the ultimate flying machine. You would need a frame that is incredibly strong, yet extremely lightweight, an engine capable of generating massive amounts of power, and an aerodynamic outer covering to slice effortlessly through the air. This is exactly what nature has achieved over millions of years of evolution. When you look at a bird, you are not just looking at an animal. You are looking at a masterclass in biological aerodynamics and energy efficiency. Let us explore how they do it. Now that we understand the incredible engineering behind birds, let us look at their defining biological traits. In biological terms, Aves is a class of vertebrates characterized primarily by being endothermic. This means they are warm-blooded and generate their own body heat, which is crucial for maintaining the high energy levels required for flight. Furthermore, they are the only living animals on Earth that possess feathers. These feathers do double duty. They provide essential thermal insulation and create the smooth, aerodynamic surfaces necessary to generate lift. Over evolutionary time, their forelimbs have been uniquely modified into wings, while their hind limbs remain highly versatile, adapted for walking, swimming, or perching, depending on the species' habitat. Beyond their external features, the internal anatomy of birds is equally specialized for the extreme demands of flight. Flying requires an immense amount of energy and a constant supply of oxygen. To support this high metabolic rate, birds boast a highly efficient four-chambered heart that rapidly pumps blood throughout their bodies. Even more fascinating is their completely unique respiratory system. Unlike mammalian lungs, bird lungs use a complex system of specialized air sacs. These air sacs act like bellows, ensuring that a continuous one-way flow of fresh oxygen passes through the lungs during both inhalation and exhalation, maximizing oxygen absorption. While the heart and lungs provide the fuel, the skeleton provides the structural framework for flight. Structurally, the avian skeleton is a marvel of weight reduction and rigidity. Many of their bones are highly fused together to withstand the physical stresses of flying. Furthermore, they feature pneumatic bones, which are essentially hollow and filled with air spaces, drastically reducing their overall body mass without sacrificing strength. Finally, if you look at a bird's chest, they possess a massive, specialized breastbone known as a keel. This deep keel is absolutely critical, as it serves as the primary attachment point for their incredibly powerful pectoral flight muscles. Understanding these incredible adaptations is not just an academic exercise. It has profound implications for both our world and our technology. Ecologically, birds are absolutely indispensable. They play vital roles as pollinators and seed dispersers, helping forests grow and thrive. As apex predators, they keep insect and rodent populations in check. If birds were to disappear, entire ecosystems would rapidly collapse due to the loss of these critical services. In the human world, the study of bird wings, feathers, and skeletal structures has directly inspired the fields of aviation and aerospace engineering. By studying how birds achieve such incredible lift and maneuverability, human engineers have been able to design safer, faster, and significantly more fuel-efficient airplanes. Having explored their biology, let us now turn to the physics that makes their flight possible. To truly understand how a bird's physical characteristics allow it to fly, we must look at a crucial aerodynamic concept called wing loading. Wing loading is essentially a measure of how much total body weight is being supported by each unit of wing area. Because birds have evolved to have very low body mass, thanks to those hollow bones and toothless beaks we discussed, and relatively large wings covered in feathers, they generally have very low wing loading. This low wing loading is the ultimate secret behind their ability to take off easily from the ground, maneuver quickly in the air, and sustain long flights without rapidly exhausting their energy reserves. This concept of wing loading can be expressed beautifully with a simple mathematical formula. The formula is WL equals m times g divided by A. Let us break down what each of these symbols means. WL represents the wing loading, which is typically measured in newtons per square meter. The variable m stands for the mass of the bird in kilograms, and g is the acceleration due to gravity, which is approximately 9.8 meters per second squared. When you multiply m and g, you get the total downward weight of the bird. Finally, the variable A represents the total surface area of the bird's wings in square meters. Physically, if the mass increases, the wing loading increases, meaning the bird must fly faster to stay in the air. Conversely, if the wing area increases, the wing loading decreases, allowing the bird to glide effortlessly at much lower speeds. Before we move on, let us see this formula in action with a concrete example. Let us calculate the wing loading for a common city pigeon. We are given that the pigeon has a body mass of 0.3 kilograms and a total wing surface area of 0.06 square meters. We want to find out how much weight each square meter of its wing must support. First, we calculate the total downward force, or weight, by multiplying its mass by the acceleration due to gravity. Multiplying 0.3 by 9.8 gives us a total weight of 2.94 newtons. This means the wings must generate at least 2.94 newtons of upward lift. Next, we divide this weight by the wing area of 0.06 square meters. The result is a wing loading of 49 newtons per square meter. This relatively low value perfectly illustrates why pigeons are so agile and can take off almost vertically from the ground. Now that we have calculated wing loading for a small bird, let us look at a more complex scenario involving a large bird of prey. Imagine a bald eagle with a mass of 4.5 kilograms and a massive wing area of 0.6 square meters. We want to determine its baseline wing loading before it catches any prey. We use our formula, multiplying the eagle's mass of 4.5 kilograms by gravity, 9.8, to get its weight, which is 44.1 newtons. We then divide this weight by its wing area of 0.6 square meters. The calculation gives us a normal wing loading of 73.5 newtons per square meter. Notice that this is higher than the pigeon's wing loading. This makes perfect physical sense because eagles are built for fast, soaring flight at high altitudes rather than the quick, fluttering takeoffs of a pigeon. This baseline calculation leads us to an important question. What happens when the eagle catches a heavy meal? Suppose the eagle swoops down and catches a large fish with a mass of 2.0 kilograms. We need to calculate the new wing loading while it carries this prey. First, we find the new total mass by adding the eagle's mass and the fish's mass together, giving us 6.5 kilograms. We then multiply this combined mass by gravity, 9.8, to find the new total weight of 63.7 newtons. Since the eagle's wings do not change size, we divide by the same wing area of 0.6 square meters. The new wing loading jumps significantly to 106.17 newtons per square meter. This physical increase means the eagle's wings must work much harder to generate lift, explaining why birds of prey often struggle to gain altitude after a successful hunt. So, we have seen mathematically how carrying extra weight impacts aerodynamic strain. Let us connect this back to the bird's anatomy. When the wing loading jumps to over 100 newtons per square meter, the eagle's wings must work significantly harder to generate the required lift. It physically explains the struggle you might observe when a bird of prey tries to fly away with a heavy catch. To survive these intense aerodynamic demands, evolution has equipped these birds with exceptionally strong pectoral muscles. And as we learned earlier, those massive muscles require a very deep keel bone on the chest for secure attachment. Every anatomical feature is perfectly tuned to handle these extreme physical forces. Now that we have calculated these forces, let us visualize them in this diagram. Here, you see a bird in mid-flight. Notice the two primary vertical arrows. The downward pointing arrow represents the bird's weight, which is its mass times gravity. This is the constant force pulling the bird toward the earth. Directly opposing it is the upward pointing arrow labeled lift, which is generated by the wings slicing through the air. The shaded region across the wings highlights the wing area, denoted by A. The text box on the right reminds us of our formula. Wing loading equals weight divided by area. This diagram beautifully summarizes the concept. The total downward weight must be distributed across that specific wing area. The larger the area relative to the weight, the easier it is for the bird to generate enough lift to overcome gravity. We have covered a lot of ground today, so let us review the key takeaways. First, the class Aves represents a pinnacle of evolutionary engineering, where every single characteristic is optimized for flight and energy efficiency. Second, their unique internal anatomy, from lightweight pneumatic bones to a continuous flow respiratory system and a powerful keeled breastbone, is built to minimize mass and maximize power. Third, the aerodynamic concept of wing loading perfectly encapsulates this balance, showing us mathematically why their large feathered wings and low body weight are absolutely essential for survival. Understanding these incredible traits not only gives us a deep appreciation for the natural world, but it also continues to inspire human innovations in aviation and aerodynamics. Thank you for joining me in this exploration of the biology of birds.